And I'll pass it over to you.
Okay, thank you. Well, I'd like to thank PYRN for inviting me here to give the talk today. And just to make sure that everything is working okay. So the slides are viewable on the screen.
Yes,
Okay,
they are.
and thank you. And what I'll do is trying to get the, oh, it's over on the other slide, sorry, the annotation for the spotlight. So thank you everyone, excuse me, for attending today. The talk will be on permafrost and linear infrastructure. And I'd like to thank everyone for attending, and also as part of the engagement throughout this discussion at the end, some people may have other expertise in some areas, and it would be certainly useful to have that discussion and engagement through open forum. In terms of the presentation today, I'm going to provide an overview of linear infrastructure. So what are these assets? How are they managed? And what's their importance for northern regions and communities? We'll try to look at linking that with the physical environment and what are some engineering considerations for the North? What's that relationship with permafrost, and what are the significance of future climate change effects that may impact linear infrastructure in northern communities? And from that, we'll look at some exploration through both case studies and also the importance of collaboration with Indigenous communities. So what is linear infrastructure? So this image here is a picture along the Hudson Bay Railway, and we'll discuss a little bit more about that piece of infrastructure later. So linear infrastructure basically are networks. They could be long linear networks like roads or railways. They could be short segmented pieces of infrastructure such as culverts or airport runways. They could also be on the right-hand side, as you see here, pipelines or energy pipelines as well. So they could be involved with utilities or the transport of energy, such as oil and gas. And basically, in terms of transportation, they could be multimodal. So they don't necessarily have to just be roadway or railway. We may actually use a mixture of those types of infrastructure components. So for example, when we look at northern Canada in the Nunavut region, the use of sea lift is quite prevalent across the region. In the Northwest Territories in Western Canada, we also use barges through the Mackenzie River to transport goods downstream towards the Beaufort Sea. We can also see in northwestern Canada, such as Northwest Territories and the Yukon Territory, we see the use of all-weather roads and also winter ice roads. So we see a prevalence of that type of piece of infrastructure in the Northwest. In terms of railway, as discussed, I'll present through a case study, the Hudson Bay Railway, which is in central Canada in the province of Manitoba. And that extends north through about mid-Manitoba up to Hudson Bay and Churchill. In the north in Canada, we have both the traditional commercial airports in Yellowknife and Whitehorse that we think of as a paved or concrete tarmac. But we also see a range of locations where we have remote airports, and a lot of these remote airports will have gravel runways. So what is the importance of investing in northern infrastructure? And we can see different components of that infrastructure here, such as the Hudson Bay Railway, the Iqaluit Airport in Nunavut, the Deco Bridge in Northwest Territories, and the Inuvik-Tuktoyaktuk Highway in the Northwest Territories. So we see different types of investment in northern infrastructure currently for northern communities. And a study that was done by the National Indigenous Economic Development Board was looking at the importance of dollar investments in that infrastructure and showed that there could be up to $22 of both economic and fiscal benefits. So economic benefits to the person and fiscal benefits to the government. So for example, through tax revenues. And that's related to education, our standard of living, our healthy lifestyles, food security, for example, as well, and also the services that we rely upon. Another study is looking at what is the combined GDP of these northern communities within the Yukon, Northwest Territories, and Nunavut. And it's around $14 billion. In 2019, the study suggested that by investing in a greater network of transportation systems for the North, it could be exceeding or could add to that GDP by about $4.5 to $6 billion with that investment. So how do we relate then the infrastructure that's in the north with the physical environment? Oops, I went backwards. Sorry, I went the wrong way. So we can look at that through engineering considerations, and some of these are similar to what we'd see in more southern locations. We have to think about the asset type and the distribution. So, is it a railway? Is it a road? Are there culverts? Are there bridges? We have to think about, well, how are we going to line that linear piece of infrastructure, such as a railway or roadway, which could extend hundreds, if not thousand kilometers. So we need to be able to assess the hazards along the route. We need to do site investigations. From that site investigations, terrain analysis, we'd look for selecting a preferred route. And for the north, which differentiates itself from the south, certainly as people are here interested in, it's frozen ground engineering is a key component. So the presence of permafrost or the non-presence of permafrost, such as talix, or other water bodies is a significant component that we have to think about. The other component that's also different in the north is actually engagement with local communities, the indigenous communities, through their territorial and treaty rights, so that we can actually get their input to the project, and also commitment and engagement throughout the life of that project, both through the design and the construction, and then also through the lifetime of that piece of asset. We also have to think about how we manage water systems, whether it's through culverts, rivers, lakes that are adjacent to that piece of infrastructure. How do we look at wildlife management? How do we look at the environmental impacts? And how do we monitor once we actually have built the piece of infrastructure, in this particular case, a roadway? One other key consideration for the north is the winter season or winter construction. And in that, it's a very remote, isolated, generally speaking, communities that we're putting this roadway through or the railway through. And how we have to think about logistics, both in terms of resources from a natural resource point of view. So, for example, gravel resources. We also have to think about human resources. Where would we mobilize the construction crew? How would we mobilize the equipment? And also, when should we conduct that construction activity? So should it be conducted only during the summer, or should it be conducted during the winter? And certainly with the ITH highway, for example, the approach was to try to limit the amount of impact to the existing permafrost terrain. And that would be through both placing the embankment, as we can see in the middle slide here, a picture, I should say, of the ITH, and also trying to prevent any changes to the vegetation cover as much as possible. With that, in the winter construction, obviously, we're dealing with sometimes limited amount of daylight, but also very cold temperatures, and we have to think about what that means in terms of both human and equipment performance. It's advancing twice for some reason. In terms of the physical environment, we have to think about different aspects, such as what differences in elevation may be through that region. So we see on the left-hand side here, the elevation profiles for the Yukon Territory, and what kind of physiographic regions and what kind of terrain units will we expect to see there? What kind of vegetation cover would we expect to see across that, in this particular case, highway network? And how does that influence both local climates or weather patterns? How does it influence the behavior of snow or water in terms of the watersheds and flooding and hydraulic bases? On the right-hand side, we see a distribution map of the permafrost throughout Canada. And certainly this is a significant difference when we look at northern infrastructure than in the south. So the presence of frozen ground, as many are aware, for more than 1 year, we can think of as permafrost. That temperature profile beneath the ground, beneath our active layer, is frozen or below zero throughout the year. This is a simplified diagram. It may not necessarily be just that we have an active layer and a lower layer of permafrost. We also might have isolated talix within that zone. We may also, depending on our location, have temperatures that are relatively warm permafrost, so close to zero, and temperatures that are more cold or cold permafrost, so say -10 degrees. And this influences how the rate of thaw will occur over time. And we certainly see some of those factors now when we're looking at both meteorological conditions, such as weather patterns, such as temperature, precipitation, snowfall, and also hydrological factors. So the runoff, for example, during the spring, or peak hydrograph runoffs when we see during the summer seasons during June and July, for example, in some regions. On the right-hand side, we see the mean temperatures for weather stations at Whitehorse, Dawson, and Old Crow. And we see on the left-hand side the location of those communities. So we're going more or less south from Whitehorse to Dawson in the mid-Yukon to the north in Old Crow. In general, we see that the overall trend is showing about a 0.4 to 0.5 degrees Celsius increase per decade. So we're seeing that, as we know from climate change, there's a gradual increase in the mean annual temperatures, both from the atmosphere or in the air. And this is also influencing changes near the ground surface temperatures and also subsurface temperatures within the ground. And that's affecting permafrost stability, primarily in the form of permafrost thaw. And from that permafrost, then, in terms of its response to climate change, we see that that can have a broad range of impacts, primarily in terms of just the physical environment itself. It's primarily threatening the way of life and their ability for local indigenous communities to sustain hunting, traditional hunting or fishing patterns. It's also disturbing ecosystems, in addition to impacting infrastructure, both in terms of its serviceability, but also sometimes in terms of its integrity or ability to actually perform its operations. So, for example, transport rail or transport cargo along a road. There's many other affecting both flora fauna in terms of those ecosystem impact. And so climate change is having, in some areas, a devastating impact on the permafrost thaw and also then the local ecosystem and physical environment. And so when we look at our experiences from permafrost thaw and climate change effects, we see that they could be varied across different types of infrastructure assets. On the left-hand side, we see problems with transporting goods using the barge system down the Mackenzie River, for example. And due to climate change effects, we see at times lower water levels, which does not allow the transit of the barges downstream. And so they had to use a detour along the highway system of 4,000 kilometers to transport the goods to the north towards Inuvik. Other cases, we see problems such, for example, a roadway in Greenland, where we see both the effects of heave and thaw, and we see this roller coaster type wavy form along the roadway. In the upper right, we see problems during the winter season. Both could either be in the fall or spring, where we have off ice, and we have these issues about water management even during the shoulder seasons of winter, with the erratic behavior of climate change in terms of weather patterns. And we also see other problems in the lower left, in the middle, I should say, and also in the lower right in terms of just permafrost terrain disturbances, whether they could be retrogressive slumps, thermal erosional type gullies, problems with water in terms of both impacting the roadway and also erosional features of that water onto the system itself. So we see that we're having problems with climate change impacting permafrost thaw, which is then in turn impacting the performance of linear infrastructure and our systems and ability to move goods or products and services to the north. And a study that was done recently by Astrid Sechler, looking at the Yukon transportation system and trying to determine the effects of climate-related costs on the operation and maintenance of infrastructure, primarily highway infrastructure and for example, culverts in the Yukon territory. The primary trend that came out of that study is a general increase in climate-related costs, Depending on how we look at the data and interpolate through that, we see different rates, but the trend of increasing costs is there. It was correlated or associated with the different physiographic regions. And in areas with greater than 50% permafrost presence or distribution of permafrost in that region, the cost magnitude increase was about double that in zones that had less than 50% permafrost distribution in that region. So we see that the effects of climate change, permafrost thaw, is definitely being at least seen in terms of the overall increase in climate-related costs for the Department of Transportation, the Yukon. So we can then think about different types of adaptation strategies, and some of those strategies are shown here, and they're mostly from the thermal perspective of how do we address climate change and how do we address some adaptation strategies for protecting permafrost in these regions.
Shawn, if you don't mind me interjecting,
Sure.
if you could explain the difference between the passive and active airflow systems in uh, in the linear infrastructure design.
Sure. So we can see a number of different options here. And certainly this is a comprehensive study that has been conducted over some time by Guy Duret and others. But we see a series of types of adaptation strategies, from a very simple one, a passive one of insulation in the upper left-hand corner. And so that strategy is useful when the permafrost is cold. And the objective is to sort of keep that thermal equilibrium of relatively cold embankments or ground beneath the insulation at colder temperatures. The detractor from this approach is that it also keeps colder air out during the winter to actually penetrate into the ground in terms of stabilizing the permafrost as well. Another simple one is just looking at shading. So in the upper right, we see a sunshed, and that does also have abilities to improve the thermal balance at the surface. And so these are very simple passive systems. The other ones can be thought of as like these, for example, in D, where air convection embankment. So it's basically a very poorly sorted, coarse fill into the embankment. And that allows that porosity to allow for a heat exchange to occur, depending on whether it's summer or winter and which direction is going to be relatively more cold or hot or warm. So it's just driving a convection cell in terms of the relative differences in density of the air. And there are other similar systems that are looking at, for example, in air ducts or heat drains, which is shown in G. Heat drains are here, which are basically a conduit at the top and the base of the embankments, a geotextile. And again, it's setting up a cell for that convective transfer of energy. And the drains, for example, in the ducts, I should say, in E or F here, they could be either horizontal in the direction of prevailing wind direction, such as shown in E, or we can set them up as a chimney duct, again, allowing for that circulation or flow. The overall improvements to the heat response certainly changes depending on what we're looking at. The simplest amount of heat exchange would be through C, such as changing the albedo. Whereas these convection cells, whether it's the air-cooled air convection embankments or the chimney ducts or heat drains, they roughly have about the same heat flux equivalents of from the studies done by Guy Duret of about 10 megajoules per square meter. And finally, we can use other systems such as shown in H of thermosiphons. And these are usually pipes that are then pressurized and charged with a liquid. And that liquid basically is at a stable point of in the ground. It absorbs the heat coming from the ground. That heats up the liquid. That evaporates into the chamber or into the column and rises through this column or pipe that's in the air. On the edges, although it may not be seen, are radiator fins that then can transmit that heat into the colder air. That then changes the temperature of that evaporation, and then back into condensate, and then that drops back into the column, and then it's a cell internal to that pipe. So these are all relatively effective systems. The air-cooled embankments, or sorry, the air convection embankments and the heat drains are roughly about the same in terms of their ability to wick heat away from the foundation. They all have different costs, with the air convection embankment to be the most expensive, but also has the longest design life. So there's trade-offs between how much heat flux can be generated in terms of releasing heat away from or removing heat away from the ground, their cost for actually construction and maintenance, and also their lifespan. So these are all considerations for a designer that would need to think about how do we actually address this properly for the condition that we see our piece of infrastructure to be built for.
Super interesting, Shawn. And before we jump into the case studies, the one other question I want to ask to help frame our conversation is, so when we're thinking about these design decisions that we're making in the North, what are some of our key considerations that we need to be thinking about in terms of designing sustainable linear infrastructure?
Well, I think for sure we have to think about in the current state, how we view climate change, and those climate change effects will occur or propagate over time in the future. I think we need to look at these adaptation strategies in the lens of being more of a dynamic pathway, so that a condition that may exist today or within the next 10 years that may be predominant may not be the case in 20 or 30 or 40 years from now. So I think we need to be able to be flexible. It sometimes is a little bit more difficult depending upon the piece of infrastructure that you have, because you need to be able to invest large capital in order to build that piece of infrastructure. But if I think about, say, for example, the Hudson Bay Railway, which is in relatively low relief, but also has a lot of water bodies surrounding it, then you may need to have to rethink about how we'd use, for example, option E, relative to where we see the water levels being, on average, being in the profile. And we'll see when we look at the pictures of the Hudson Bay Railway, the embankment level and the water level are very close. So some of these systems may naturally not be selected because of the environment that you're in. But I think the primary one is, historically, when we look at designs in the Arctic, we looked at the stability of permafrost as a positive aspect for our design, and we utilized that and integrated that into our design. And that's not necessarily the case anymore. Definitely some regions may have local cooling, but on average, we see permafrost thaw happening. And how that's going to affect both the mechanical behavior of the soil, but I also think as we move forward in some areas such as Hudson Bay, how do we view the hydrological cycles and hydrology itself?
Awesome. Thanks so much. I think we'll pass it back over to you to keep going.
Okay, thank you. So what we see out of that is there's interconnected relationships that we need to think about, and it sort of follows on from that discussion where not only do we just have to think about the one hazard, so for example, permafrost thaw and subsidence, but how do we think about snow during the winter, and how do we manage that precipitation, which is more uncertain in terms of predicting what will happen in the future. We have a good handle on how temperatures may change under climate change events, but not necessarily on rain or snow precipitation and also their intensities. But they all play an integral role with one another in terms of how we manage the snow, because that influences how cold may penetrate into the ground if we have embankments of snow adjacent to the embankment of the road. How that influences water flow during the shoulder seasons, both fall and spring, and how we control that icings or glacier control on that system. And what do we do in terms of managing water? So during the winter, for example, some of these culverts could get stuck or filled with ice and snow, and they may not serve their purpose immediately during the spring. We may then get slides or slumps and washouts and need for repair. And so what we can do is then look at that through two case studies. One is on the Hudson Bay Railway, as we see here on the left-hand side. So we have a drone shot of that image there, where we have a bypass. There's not that many along the rail, but this is one of those. And on the right-hand side, a second case study is in the village of Mayo in the Yukon, in the traditional territory of the First Nations of Natchitoches. So when we look at the Hudson Bay Railway, it's located in Manitoba, so just west of Ontario in sort of central Canada. The railway itself is going from the Pas up north through to Churchill Bay, through to Churchill and Hudson Bay. So that's going from this range here in central Manitoba. It originally, the thoughts about constructing this railway started in the mid 1800s, primarily to get goods such as wheat or other products such as beef to market in Europe. And it was looked at as a shorter route from Western Canada, such as Alberta and Saskatchewan, through Manitoba and out through Hudson Bay towards England, rather than going all the way through the US to New York and out. And so the idea was to build this railway initially it was to Nelson here, but that has problems of sand accumulation at the mouth of the Nelson River. So the thought was then to move it northwards to Churchill. And some of these images here are from the early 1920s, when construction began in 1910, was halted during the First World War. And finally, the Hudson Bay Railway itself was completed in 1929. And the first shipment of grain was out from the port of Churchill in 1931. So I see some old images here about how the railway was built, and we can see something similar to the ITH highway, where the embankment of the railroad itself is relatively level with the terrain, and maybe on the order of 1.5, 2 meters high. And if we look through the Hudson Bay regional physical environment, we see a demarcation of post-glacial marine submergence here in the dash line. So glacial lacustrine versus glacial marine type conditions. We see variations in the type of terrain units, such as organic layers, fen, or peat plateau, as we're moving from Churchill going south towards Gillam. And we see eventually we'll run into, as we get more south and near Gillam, where we get into the Shield and boreal forest. Also, another aspect of that, because of the historical nature of this area in terms of glaciation, we also see as we move from south from Churchill towards Gillam, we see that the peat thickness is increasing with distance going south, anywhere from 25 centimeters and varying up to 400 in some areas. With beneath that, we'll have mineral soil as well. And although, for example, in Churchill, we see that the left-hand side of the image here near Churchill, we see that it's classified as subarctic boreal transition with bog and fen and minor swamp. This image or picture here on the right is actually just outside of Churchill, and it's one of the first culverts along the HBR, the Hudson Bay Railway, that we see coming out of Churchill. So there are some minor variations locally, but the classification in general gives a good description of that area as we move from north from Churchill to south along the railway. So what are some of the engineering challenges that we see? The primary one, as we see, is in the center picture of a core taken out from the soil itself. So the project, and I'll get into some of that detail later, did a series of geotechnical boreholes to extract soil, a core or cylinder, and we can see the soil samples itself interlaced with ice lenses. And certainly the permafrost, or the existence of the permafrost itself, is a significant issue and significant engineering challenge. And it has been since the railway was constructed back in 1929. The main ones are related to accelerating permafrost thaw due to climate change effects, and that's causing deformations within the railway embankment itself, and that might be due to vertical changes in its elevation or subsidence, which are also known as sinkholes, or classified as sinkholes from the Hudson Bay Railway's perspective. But as also, as you see on the right-hand side, depending on how it's interacting with water and flooding and washouts, we also may get some lateral spread. of that material as well. And we also see here along the right-hand side picture of that wavy nature through that subsidence and change in the profile of the railway itself. In 2017, there was a significant flooding event, which cut off Churchill for some time through the summer month of 2017 until the fall. And that caused significant washouts and flooding, major damage to culverts and some bridges. And also there are other issues with bridge foundations as well along the route itself. And so from that PermaRail, which is a multidisciplinary project, it's in collaboration with Hudson Bay Railway and the Government of Canada through Transport Canada. And it's a consortium of people from the University of Laval, Carleton University, where I'm from, University of Calgary, Queen's University, and the Royal Military College. The Arctic Gateway is also a company that is also an umbrella company. Sorry, Hudson Bay Railway is an umbrella company underneath the Arctic Gateway. And the overall project itself for PermaRail, we're looking at a major project over till 2027, where we're looking at both physical geography and understanding the terrain, understanding, for example, how lakes drain, understanding the impact of an evolution of ice wedges, through to looking at how bridge piers are experiencing frost jacking, and then also looking at other issues related to hydrology and also related to geomechanical behavior, as you'll show in the next couple of slides. So it's a major project with a lot of expertise from across these institutions that our main goal is to try to help the Hudson Bay Railway make better informed decisions about the effects of climate change on permafrost thaw and the performance of the railway so that they can come up with adaptation strategies and better decisions for the future. One study that's being conducted is looking at flood hazards. And as we can see here, there's a significant impact on the left-hand side. You can see of that flood event from 2017. This is after subsidence of some of the water has been drained away, but it's still up on near the top of the embankment and also still within the trackway itself. The effects of that washout is shown also on the right-hand side here, where you can see that some of the track is suspended in the air. And from that, they had to go back and obviously replace the embankment and go back and replace any culverts, and also in some areas add new culverts, as we see in the middle here, and put it down in some geotextile to try to provide some lateral support. In a lot of areas, they also put down geogrid to try to give that lateral stability as well on the embankment. So I have a master's student, Adela, who's looking at a number of issues. One of the first studies she did was looking at basically the susceptibility and vulnerability of the railway to flooding events. And supervisors are Dr. Elise Devois from Queen's and Dr. Marie Richardson, who's also from Carleton University. And she looked at basically the distribution of fens and bogs along the railway, the drainage patterns and network that's associated adjacent along that railway within the watershed, and also the presence of ground ice, and then looked at combining those indicators for susceptibility or vulnerability of the railway and produced this map here. And generally speaking, as we're moving from south in the PAW, going north to Churchill, these vulnerabilities where we're going from 0.75 in the scale up to 4.25, which is high vulnerability, are consistent with what we've seen from the 2017 flood events as well. Another study that she's looking at right now, which is using basically the hydrological model, which is R, Raven, programmed in R. So she's looking at calibrating the simulation with observations from a gauged river. The difficulty in this area, although the watershed is relatively large, we have very few gauged rivers. So in the past spring, we actually instrumented some of the smaller ungauged rivers, and we'll go through that process of looking at that data in the coming years. But she's been able to produce or reproduce a very good simulation of the watershed and region, as you can see here, where the simulations are in red and the observed data is in black. There is some issues at the beginning when we're looking at the spin up of the model to get to equilibrium conditions, but she's captured most events quite well in terms of the peaks. And we're looking to see how we can improve that simulation in the future going forward by collecting additional information from other ungauged rivers that we just recently instrumented. Another study is looking at how do we predict the behavior of the soil and the embankment of the railway with continued climate change and permafrost thaw. And this is looking through coupled numerical models that are looking at both the thermal and geomechanical response of the soil and of the embankment itself of the railway. So this is a drone shot of one area where we have a large water body that's drained parallel to the railway itself, and another series of shallow water bodies adjacent to that railway. So Gina Rezzani is looking at conducting a PhD, doctoral studies, and looking at developing this numerical model in a software called Abacus. And so she's basically looking at modeling the embankment, more or less as a gravel. The adjacent terrain, excuse me, in the upper couple of meters can be classified mostly as organic and peat. And beneath that, we have in some regions a silty clay layer. Below that graphic or image of that profile that's being modeled is the finite element model itself. And this is just some of the preliminary results where she's looking at calibrating the numerical simulation for the thermal gradients penetrating into the soil over time based on the climate record for both historical weather patterns and data, and also looking forward in the future as to how we expect that to occur over the next 20, 30 years based on projected climate change effects in terms of the climate patterns. One of the key issues will be trying to better determine how the soil will respond. And that's also including some effects about what's happening internal to the soil itself. So although the soil may be frozen, there will be some water content within that soil, depending on the temperature, that's unfrozen. And as the permafrost thaws, if we have excessive ground ice, then that water, then as the permafrost thaws, that ice will change into water, which will then be within the soil itself, but above the availability for that soil to actually carry that water. So then, in part, the soil has lower shear strength or lower ability to carry load and will deform. And so her objective is to basically improve some of these constitutive models that define how the soil will behave under those conditions so that we can better anticipate or predict what may happen in the future. The second case study is looking at the First Nation of Natchinukdun, which is in the Yukon. And there's three studies across different scales. And this is being conducted by a PhD student in the Department of Geography and Environmental Studies here at Carleton, with myself and Dr. Murray Richardson as the supervisors. Frederick is looking at both basically infrastructure within the village of Mayo, also a larger scale along the Stewart River watershed and Natchinuk, and also across a broader scale across the entire First Nations of Natchinukdun traditional territory. And so we're looking at different scales for these studies. One of them is looking at the infrastructure within Mayo, and we have some limited data sets, both in terms of past LiDAR data sets, some boreholes where we have some geotechnical information, and also we've done some aerial drone surveys, so optical, and also have done a couple of electrical resistance tomography transects, such as shown here by the yellow lines. And so we have some limited data from the past that's being combined with current studies that are being conducted by Frederick. And from that, at least so far, he's able to then establish terrain disturbances. And over time, in the near future, we'll also be able to establish a better understanding of what that actual displacement field is. So for right now, we have a relative effects of where the regions are heaving in purplish blue and where areas are subsiding in the darker red colors. And these are, in terms of the behavior, it's also consistent with the boreholes that are there. And so the boreholes, for example, in borehole 2 here, for example, where we see the highest subsidence, That has ice-rich permafrost with a depth up to about 7.5 meters, whereas borehole 6 has no permafrost, at least within that borehole, the shallow borehole that was drilled. In borehole 5, we have permafrost as well, down to about 5 meters. And from that, he's also then be able to look at the presence of frozen ground through electrical resistance tomography investigations, and is able to then establish an expected area where we see some ice-rich zone and also some probably thawed zones here in the yellow. So the darker the blue represents ice-rich or permafrost zones, and the yellow represents areas which have an expectation of no permafrost being present. So we're able to then use that information, and this is really would be helpful in terms of providing that information to the Village of Mayo and also to the FNND, so that they could actually use that in self-determination, so that they can actually think about how they want to use the land and what kind of plans that they will use for their needs going forward, and how do they want to express in terms of what they perceive as their needs, and believe that this is the best way forward to meet those needs. And that comes into then engagement, collaboration, and co-creation. So I'll put up, I just put these two quotes here coming from an Arctic Northern Policy Framework a few years back. But I think it's still relevant and it's still important to think about. So it's one from the federal government's perspective of the Crown Indigenous Relations and Northern Affairs, or CIRNAC. And I think the key is that we're looking at supporting and co-developing these solutions really from their perspectives, reconciliation, and providing them with the capacity for self-determination. And it's really about how we need to be thinking, both in terms of active listening and engagement, so that we fully understand and appreciate the perspectives of the Indigenous communities, and so that we can actually meet their needs. And when we think of, in this case here, a quote from the Gwich'in Tribal Council, their needs or their desires to have direct representation, that they can address issues that are important to them, and moreover that they can bring then in their Indigenous knowledge into that, and we can then combine or integrate both traditional Indigenous knowledge, our perspectives from the way in which we train as an engineer or scientist, and hopefully we can then collaborate and engage such that we can actually leverage that and make the best of the opportunities. And so through engagement, we can get better perspective on Indigenous priorities, how they view their relationship with the land, how do they view their stewardship, what's important to them and their culture. So we all have our own perspectives, we all have our own backgrounds, and the way in which we develop and think. And we really need to take that into consideration and not impose these things into communities in the North. And from that, if we really actively and purposely listen, we can build that trust and build those long-term relationships. We can then collaborate. So we all may have different perspectives. Some may be empirical, some may be very theoretical, but we all can share our knowledge and our expertise. They live there on the land. They use that land for their traditional way of life. And from that, we can also then, as we think about doing these studies in the North, creating these research studies that we think of from a scientific perspective to be important and to drive something that we believe to be helpful going forward, but we can also then learn from them to understand how we can best build that capacity, so that they can use that and for their self-determination, for them to understand how best can they either both collaborate but also independently drive those issues forward and address their needs and priorities. And from that, we can co-create that knowledge with that direct community involvement, both through engagement and collaboration. We can integrate that traditional knowledge into our scientific understanding of what's happening. And I think overall, and that's the best way forward in terms of how we look at both addressing those needs for the North, but also like from our perspective of an engineer or a scientist looking at a problem of trying to actually solve a particular issue. But we really need to think about that engagement with the Northern communities. And certainly in both of these projects, there's direct involvement and engagement with both Natural done with an agreement actually through Carleton, with Carleton University, to do that engagement, and with Hudson Bay Railway, which is an Indigenous-owned company with both and the northern communities within Manitoba. And so it's important that we actually develop and build those relationships going forward. And so with that, I would like to just conclude that linear infrastructure are key assets, whether we're talking about the north or the south. The climate change effects on permafrost in particular is a significant threat. And with the expected trends, permafrost thaw will continue to impact the north. And that'll be just through even just the geomechanical thermal response. However, I think in the future, as in particular along the Hudson Bay Railway, for example, the importance of surface water flow, the drainage patterns, how they may change, how does the permafrost thaw affect both permafrost and the location of talics? So do disconnected ponds today link up in the future and cause changes in those drainage patterns or cause changes in those flow and flood patterns for the future? And how does that impact groundwater flow? And I think in some areas of the north, this will have greater significance in the future, rather than the way in which we traditionally think about permafrost, which is basically a thermal mechanical problem. I think in these areas, it'll become a thermal mechanical hydrological problem. And I thank you for your interest and attention for this discussion, and look forward to our discussion.
Thanks, Shawn. Really informative, and really appreciate that you put a lot of visuals up there. It helps with showing the physical phenomenon you're talking about. At this time, we can open up the question period to everyone else to see if there's any questions for Shawn. I don't know if they can speak or if that has to be typed.
You can ask your questions in the chat or in the Q&A, or if you raise your hand, I'm happy to unmute whoever would like to ask a question verbally.
And I also think, if other people have experiences, maybe not the direct questions, but if you have experiences that are related to this, I think it's also useful to have that discussion as well. Certainly, that adds to everyone's knowledge.
Absolutely.
I guess while we're waiting, we can start off with the question. So what would you say is a huge difference between, let's say, buildings, structures versus linear infrastructure?
At least, certainly historically, the biggest differences would be in the site investigations in terms of the amount of knowledge that you have. So typically for a foundation of a building, for example, we would have a very significant geotechnical borehole drilling program and site sampling program so that we'd really understand the characteristics of the soil and what's physically present underneath that building. Within long linear infrastructure, especially like railroads, roadways, pipelines, which can be upwards of hundreds or thousands of kilometers, we usually only have information that comes from terrain analysis, so a very macro level. But these people that specialize in terrain analysis can do a very good job in terms of understanding the high level behavior and what's expected in terms of maybe the presence of permafrost, the not presence of permafrost, how much ground ice do we expect to see. But it's still at the very macro level. Along each particular kilometer post, for example, we won't have that much information, and it might only be a few boreholes for a few hundred kilometers. So we'll have very limited detailed geotechnical information on which to base our design. And I think in terms of, so for example, in the ITH, I think they went through a bit more rigorous way of collecting boreholes and collecting site investigations in terms of information about the geotechnical conditions. And certainly as we see this infrastructure, although the Hudson Bay Railway itself has survived in operation in some form since 1929, it's still undergoing challenges to permafrost thaw and subsidence and sinkhole development. I think it will undergo also increasing threats from hydrology in terms of both flooding, washouts, and the interactions of water bodies. It's still important to understand what's happening subsurface and to get a better understanding, because if we can design that at the beginning, it's less expensive or less costly than if we start then to think about adaptation strategies after it's been constructed.
Do you think that because when they did the initial install, it was a different story back then when they did the geotechnical investigation, there's more ground ice, whatever it might be, and now the, let's say, water courses are have changed. Um, if
Well,
that's something
yeah,
that's not preventable.
I'm not sure if the water courses have changed, but certainly when, for example, the Hudson Bay Railway was first constructed, um, there would have been limited, if no, geotechnical investigations conducted from, for example, boreholes. But the surveyor might have had some knowledge about geotechnical conditions based on visual inspection of the area, or maybe hand samples or bucket samples. Um, and certainly they've had challenges when they were building it because they weren't sure whether they wanted to go to Nelson, which was shorter, but it had a significant problem of dredging. So initially, the cost differential for the project was about 3 to 1. So it's about $30 million if you built it to Nelson, and about $10 million if you built it to Churchill. Albeit Churchill has longer term annual recovering costs because it's going through such hazardous terrain in terms of the stability. Um, Going to Nelson, it would still have an issue, but it'd be primarily a dredging problem.
We have a question from, I want to say ABK. I'm not sure if I pronounced that right. I apologize ahead of time. They're curious about wastewater systems. The so wastewater, they want to know if there's specific concerns for design in over permafrost. So I suppose it would be more related to the pipelines if they do carry wastewater in the communities.
It's a good question. It's not an area that I know much about. I do know that recently they seem to be having more failures of their wastewater systems. But the basis for design and that for the north, I'm not that familiar with. Certainly in the south, we try to get everything below the frost line, so within that below the active layer. So yeah, unfortunately, I don't know the details of that design process.
If it was wastewater being carried in a pipeline, would it have similar requirements to say hot oil passing through a pipeline, where you just have to make sure it's above a certain distance away from the ground so it doesn't cause melting?
Well, certainly if it has a heat signature, the general design conditions or approaches, at least for energy pipelines. So if we talk about oil pipeline, the general approach is to build it above ground if you can. And if I go back here, for example, you'll see on the right-hand side, this is the TAPS, a Trans-Alaska Pipeline System. And this is built above ground, primarily because it's an oil pipeline. And you want to then prevent that heat signature from affecting the permafrost below. The thermosiphons you can see here in the foreground, and so you can see a column where that charged fluid is, and then the radiator fins here, which are then allowing the heat to escape into the atmosphere. If you have a gas pipeline, because gas pipelines, no different than say your propane tank, as your propane tank gets lower in terms of the amount of propane that's in it, you feel that condensation and coolness on the outside of the tank. That's generally colder than zero. And the problem with gas pipelines, you will bury it, but generally then the problem is frost heave. So for oil pipelines, it's thaw settlement. For gas pipelines, it's frost heave. The other nature of this, you might ask, is why is it has this little zigzag pattern? That's in part one for thermal expansion, but the other is also this is in a earthquake zone, so it also allows it to have some flexibility for deformation capacity during a fault movement.
Yeah, really interesting. There's another question. I'd like to know a little bit more about different types of linear infrastructure. I remember you mentioned transportation, utilities, and energy, and something else. Would you be able to remind me and go back to the slide? Also, do you have any more information or examples on more types of linear infrastructure?
I'm trying to recall what I was saying. Certainly in terms of transportation and for linear infrastructure, I think primarily we think about, or at least I think about, is railways, roads, and pipelines. And these are generally long, extended pieces of infrastructure, hundreds to 1,000 kilometers. Culverts, airport runways, they can be thought of as linear infrastructure, but very segmented and very isolated or locally um, um, determined. We can also, water utility networks are also other types of pipelines, but they're typically within, a suburban or developed area. The other ones in terms of utilities we could think of would be fiber optics as well. That's also a piece of linear infrastructure or transmission lines, for example. I don't have much knowledge about those types of pieces of infrastructure, but certainly I couldn't find a good picture to show, but along the Hudson Bay Railway, at different offsets, there is a new fiber optic cable that's actually installed that goes up to Churchill.
There most certainly is. I've seen the flags.
Yeah.
Um, okay, so the next question says, what considerations are in place for long-term settlement associated with infrastructure in Arctic regions? Or is there any considerations that we've been giving to this sort of a problem?
I think there are general considerations, and I think it depends upon the asset as to what's governing. Certainly, if we think about bridges, and Natalie, you would know more than I, but certainly as civil engineers, we think about bridges or other structures as beams. There's a certain deflection limit relative to its length that we have to meet. So those are sometimes the more rigid codified ones. Settlement, even with buildings or any other pieces of infrastructure, aren't necessarily detrimental. The detrimental problems usually occur is when you have an area that's not going to settle. So the differential settlement is usually the issue, or the curvature or the rate of settlement, for example, may be relative to a portion that's not settling. So when we think about pipelines or the railways, the railroads, railways or roads, um, it's the differential settlement that causes the most problem. So areas that are not moving versus areas that are moving, that's usually the limit. Now, where we define that limit, it depends upon the owner of the asset and what's acceptable in terms of their performance limits. So, for example, the railways, they're governed by Transport Canada regulations, and they'll put specific limits on how much settlement per unit length along the railway is allowed to occur. How much difference between the left track versus the right track in terms of its relative elevation. So there's sometimes rules of thumb, sometimes codified or standards rules about what that deformation limit is. So for the TAPS pipeline, although they are governed by the US Code of Federal Regulations, by ASME design codes, some companies may impose their own restrictions that may be actually above those codified or design standards because they look at it from not necessarily a technical risk, but an economic risk. So can I afford for this piece of asset not to work for X amount of time? And so then you base your business model on that. And certainly when we think about the Hudson Bay Railway, it's the only land transportation that gets into Churchill. So depending on how you view that to be important, then you may change your design criteria for that or operation maintenance criteria because of that.
So it's 2 o'clock now. We do have a couple other questions, but just to respect everyone's time, for people who came for the technical webinar, you'll get your professional development hours. We'll be moving into our informal discussion now until 2:30. So if you have somewhere to be, I really appreciate you guys coming in. Um, just go over quickly what we talked about today. We went over the importance of linear infrastructure in cold regions. Um, we went over the susceptibility and vulnerability of infrastructure in the context of a changing climate, so many different examples. We looked at two different case studies, the Hudson Bay Railway and then the two communities, Nacho-Nyakdun and Nacho-Nyak-Tage, and the importance of research focused in the communities. And also we went over the importance of collaboration with different stakeholders. So again, PDH will be provided for this hour, and then we'll be moving into our informal discussion. For the questions we didn't get to, we have two questions here. We can bring them up at the end if you want to stick around for that. I'll pass it over to Natalie again to kick it off for the informal discussion.
Okay, so what we're hoping to do in this part is just to have a quick discussion about Shawn's background, how he ended up doing what he's doing. So it would be great, Shawn, if you could talk a little bit about how you ended up researching linear infrastructure, how you ended up in permafrost, and the path that you took to get to where you are.
Sure, thanks. And yeah, it's certainly something that I think could be a discussion rather than a presentation as well. But overall, I think in some ways a non-traditional path to where I am today. I think that sums it up. I've been across both consulting, engineering companies, applied research organizations, and then eventually, as I am today, in academia. I started out basically as a civil engineer, thinking that I'll get a degree in civil engineering. I was interested in structural analysis. I'll go out into the workforce, get my PN, and I'll be happy. I happened to then, at my time when I was at Memorial University, I'm from St. John's in Newfoundland. So you can see Cabot Tower up in the upper left. On a normal day, so that's a summer day, foggy, not that warm, but warmer than here it is today in Ottawa, at least, anyways. I got interested in research because of the work term co-op program there, and I worked at the National Research Council here in Ottawa, and was doing work using finite difference technique on the fire resistance of reinforced concrete columns to structural loads, and obviously heat from the fire. And that got me interested into numerical modeling. And then I was always had some interest in terms of ice engineering and the Arctic, and a little bit on ocean engineering, such as coastal engineering. So you see in the lower right here, a breakwater in northern Norway. And so that got me looking at how can I get between my bachelor's and my master's, how can I get to some work experience in an interesting place when I know I'm going to come back to St. John's and do my master's. So I managed to get work in both Norway for the summer in the northern islands of Lofoten Islands on the northern coast of Norway. And the main area there was a town called Kabelvåg. And I worked for a company of Kystverket, and that's more or less a mixture between fisheries and oceans and Coast Guard and public works from a Canadian perspective. So we dealt a bunch of things with dredging, breakwaters, demolition, blasting, surveys, bathymetry, and so on. And that was a very nice experience. But the primary reason to go into Europe was to go to Helsinki University of Technology because I was interested in ice mechanics. And Helsinki University of Technology here, that's the main library there, and that grainy scanned photo in the upper right. So it's a nice campus, and it's a very interesting but expensive city to live in. And the pictures in the middle are on the ice engineering tank in St. John's at the Institute of Marine Dynamics. That's changed name, but and then this one here in the middle is Hobson's Choice Ice Island. So for my master's, I was able to go up there, and you can see the camp here roughly in the middle. And so we've had a runway built there, and so as a camp on the that was run by the federal government, and the intent was that was going to be a floating research station that would just go around the Beaufort Sea Gyre and collect data. And so for that, we were doing some experiments, and you can see this large indenter here crushing into the ice wall. So we dug a trench into the ice. So that ice island was about, from stretching my memory now, but about 1,200 meters long, about 75 meters wide through the glacial part of the ice island. The rest was then covered by multi-year sea ice on the outside perimeter. And so along that central portion, we were doing these tests, and this was an industry-sponsored research program. And so we're looking at the forces on ice structure interaction, and that's where I wanted to go into. In the late 80s, there was an economic downturn, so then I pivoted to an area of impact buckling for my PhD, primarily numerical modeling. From different contracts with different organizations, I eventually went to a company in St. John's Newfoundland called CCOR, which is Applied Research Organization. And that got me down the pathway of more or less where I am today, which is pipe soil interaction. And so now in general, some sort of structure soil interaction, primarily from the numerical modeling sense, but also now getting more into physical testing, whether it's modeling using geotechnical centrifuges, and also field studies. So using a lot of geophysical instrumentation, such as ground penetrating radar, electrical resistant tomography systems. So it's sort of spread out the area of research and the area of interest in terms of new experiences, but certainly not a linear path. And other aspects, I was working in Houston, working on because of my experience in pipe soil interaction. I was working on projects that were looking at Arctic gas pipeline developments, both off Sakhalin Island in the Soviet Union and gas pipelines project in Alaska and in Canada.
What would you say between when you first started and now, what are the biggest differences in engineering and working in the Arctic? Like, what are those over those 20 years? What's the biggest things that have changed, do you find?
Hmm. Well, I guess probably the biggest change is the not necessarily expectation is probably not the right word, but there's more demands, I think, on students right now because there's obviously a history that's been built up, and that incremental build up of knowledge has helped. But at the same time, it's becoming more in depth and more detailed and more specific. So people are very, as you study, you're developing something that's a very niche area, whereas in the past, if you go further and further back, it's more broad. It may be new and it may be unique, but it was a bit broader. So I think the challenges for present day students is the depth at which everything is being drilled down into, and to develop those systems, whether it's a physical model, numerical model, unique contributions, and so on. I think in general, from a practical sense, the primary issue is climate change relative to the previous talk. It's, the presence of sea ice, for example, as a problem for offshore structures to deal with is becoming less relevant and prevalent. There still will be multi-year sea ice, but in some regions there may not, sorry, there still will be first year sea ice, but in some regions there may not be multi-year sea ice anymore. And multi-year sea ice or these large ice islands, such as these calved off Greenland or northern Ellesmere Island, may not necessarily pose the same risk as they used to. So there are different challenges, and I think primarily climate change driven. As we go back to foundations in permafrost, for example, the assumption that we can maintain that stability and use that as a strength for the design may no longer hold true. The other big aspect is, I think, the availability of numerical models and tools to actually assess some of these items. But then that in itself requires a very steep learning curve and a lot of experience to be gained to use it properly as we look at more in-depth type studies and development. So it's sort of I mean, I guess in some ways like the origins of Wikipedia or ChatGPT, it was broader based. You might not necessarily believe all of it, but as you build up information, you get better understanding. It gets more refined, it gets better understood. And so some of that, I think, as we're moving forward, aspects that we didn't think were important before are now, based on people's research, are becoming more important. So, for example, the presence of talics, for example, beneath the active layer. In the past, we would have had a very simple definition of, well, you have this very simple layer of active layer, and that's active during the spring, summer, winter. And below that, you have permafrost, and there's no real irregularities or pieces of soil that are basically unfrozen. And so how does that influence the thermal behavior? And then how does that influence the hydraulic behavior? So a lot of these issues are now unraveling and becoming more complex to understand and to develop a model.
That's really interesting, Shawn. I think one of the other questions we kind of wanted to get into was how did you find yourself in getting interested in ice and permafrost and geocryology in general?
Yes, I was thinking about that as well as in terms of like my initial interest for sure. It might be, I don't remember exactly how I got it interested into the Arctic, but certainly I remember being, at least when I think back, mid-engineering, I was starting to develop an interest in Arctic and Arctic technologies. And um, I guess maybe because I was just thinking or debating between civil versus naval architecture programs at the time. I eventually went into civil because I thought, well, there were certain structures in the Beaufort Sea that could be designed, and that typically was designed by a civil engineer because you usually put a structure out and filled it with sand, for example, to give it stability, to resist the ice forces and mass. So but I'm not sure what germinated that initial interest. The Definitely the interest in the Arctic from a perspective of permafrost and cryology was the work when I joined Secor, and they were primarily interested in looking at how they could support oil development and gas development, both in the province of Newfoundland and Labrador, and that has the problems with ice interactions with the seabed offshore, but also with Jack Clark, who is a geotechnical engineer and a well-known leader in the permafrost community, and also across Canada in the Canadian Geotechnical Society. And that got me interested in issues related to both permafrost thaw and also permafrost heave. But most of the time we were dealing at that time was permafrost heave because we're dealing with gas pipelines. And so most of our research and work that was being done was looking at how to make sure the pipeline could sustain integrity with large heave movements of meters to 2 meters height. And again, the problem is not necessarily it's a 2 meter height movement, it's that other parts of the pipeline may be going through discontinuous permafrost regions and they may be anchored. And so it's a differential movement of that pipe. And so we were using both numerical modeling and geotechnical centrifuge modeling to try to assess those problems. And it was an interesting in terms of a mix, in terms of both applied research and development for commercial interests, in that case of gas developments, but also some parts of academic research because we had to prove some of these numerical models and develop them so that we could actually have confidence in the outcome. But I think it's more as opposed to a eureka moment. I think it was a broad, gradual transition and evolution of that interest in different fields, and having experience with both people in industry, but also others such as Ross Mackay and Dundabs, because we're also looking at issues about what we see today in terms of if we disrupt or damage the organic mat and the vegetation layer and cover of the permafrost terrain. They were looking at physical studies of how they could actually reclaim that land back and revegetate the terrain so that we can stabilize permafrost thaw. Because even at that time, even though we may think that the climate change effects weren't going to be as significant as they are today as we see them, by digging a trench and ditch to bury the gas pipeline, we automatically disrupt that thermal equilibrium that was there. So then we're looking at studies of how we can actually re-establish that thermal equilibrium as quickly as possible.
Super interesting. I think to kind of wrap this part up, and then we'll circle back to the remaining questions we had, and any other questions that might be floating around in people's brains. I think the last thing I wanted to ask is, do you have any advice for people that want to get into Arctic engineering, career perspectives, grad studies, so on and so forth?
I think it's a really good opportunity at this stage because of the threats that are happening from climate change effects. Not even just from an engineering perspective, but it's having widespread influence and impacts across all spheres. We can think of it from a social science, we can think of it from biological and ecosystems. And certainly at the last ArcticNet conference here in Ottawa, although some of the discussions deal with engineering perspectives, a lot are dealing with social and biological systems, ecological systems, and so even just something to learn about that I can't remember the name of the species, but there's a bird that actually is having a really difficult time because of climate change and temperature rise, the amount of work rate that they're doing to get food, it's causing distress to the parent. And so that species is really struggling. So it's, I think, across broad classes of science, even if it's in the human geography side or social sciences side, I think it's an important issue to think about going forward.
Yeah, that's great. Okay, so I think we're going to circle back to there's two more questions in the chat that we didn't have a chance to answer. And then if anyone else has any other questions that have come up while we've been chatting, feel free to also drop them in the chat. The first one was, do you think that artificial intelligence will play a significant role in linear infrastructure, particularly in areas like monitoring and maintenance?
Yes, it will. I think it'll have a greater role as we move forward, and in some ways we already are using that, depending on what kind of routines we're using, whether it's machine learning or other types of ways in which we interpret optical images, radar images, LiDAR. So we're using that in present form. I guess it really depends on how you define artificial intelligence. I would argue, in some ways, I would argue even the programming that I did is some form of artificial intelligence a long time ago, even just using Fortran. But in the context, I think, of the question, that I think it will get much greater influence as we move forward. I mean, I use it in the sense of within the class setting to actually show its capabilities or highlight its capabilities, and also we still have to be at least the simple chat GTP type artificial intelligence. We have to be careful about how we view its responses. Some of it's pretty good and spot on, but a lot of it is not correct as well. So we have to, in terms of that sense, we have to be careful about how we use that form of AI. But I think in terms of the other aspects of how we use it to interpret images, to do structural health monitoring, I think that's just going to carry on and be more significant in the future.
Yeah, really interesting. Okay, and then the last question here was, do you have any thoughts on how to protect existing structures, particularly of historic importance? And then it says, how does agriculture play a role in understanding permafrost long effects on linear infrastructure? So maybe.
So in terms of protecting infrastructure, I think it really depends upon the context and what are the main hazards. Certainly, if we think of climate change effects, and that has one particular aspect, but we still have other natural hazards, whether it's in a seismic zone, whether the soils that surround it could be liquefiable or flow easily into that seismic action. Are we dealing with areas that have permafrost? Is it adjacent to water bodies, or how do water bodies influence the local region? So I think there's many different ways that we can think about how we protect infrastructure assets. In some areas, so for example, if we have severe coastal erosion, you may be limited. And certainly when we look at the areas just off Tuktoyaktuk, there are significant areas of coastal erosion. I'm trying to remember, there is also I shouldn't remember the name of it, but there's also a fort in Manitoba that's having problems, that's run by Parks Canada, that's from the origin of Hudson Bay Company.
Oh, is
That
it
is
the one
having
in
issues.
Churchill? Yeah.
Yeah, like for some reason I've lost the name of it, but that I know they've been looking at adaptation strategies and ways of protecting that structure, but I think parts of it it's still difficult to maintain its integrity. So I'm not sure where that project is, but I do remember reading something about it a few years ago. The second one was on agriculture. What was the
I
context?
don't know if the person who asked this question is still here, because perhaps they could maybe clarify. I would take it to mean the surrounding vegetation, most likely. I can unmute you if you want to expand on your question.
Hello, hi. So my question was related to the because the vegetations on the Arctic zones are quite different. So I wanted to know, does this play a role in the effects and of the existing structures which are already present? Do you change the strategies to protect them? If or what are the effects of this agriculture on this structure?
Right. So it's not. So you're talking about just the vegetation as opposed to an agricultural production, I guess. Um, Certainly, they inform how you should address different problems in the areas because they'll provide you with indications of both subsurface conditions um, and also whether or not you expect to see in the permafrost region, for example, that it's either relatively stable or is it undergoing transitions. And we see this along the Hudson Bay Railway, where we may see in the north wedge polygons that exist. And as we move further and further south, we'll see that there is a transitions between peat plateaus and the fens and bogs. And that gives you an indication of that there is some disturbance that's happening subsurface and a transition in that area that may then influence both how disconnected water bodies in a permafrost area, as that permafrost thaws, do they become connected? Do they then maybe cause other issues such as thermokarsts in an area? Do they drain lakes in some regions? Do they alter surface water flow, or do they alter subsurface hydrogeological flows? So I think in some ways, I think to answer the question, if I got it correctly, we can certainly use information about the terrain and the vegetation to give indications about what's happening, and that they may inform us how we want to address infrastructure protection or operation and maintenance. I mean, I know in general that the vegetation is changing, going south to north, and so that species that were not there decades ago are appearing. No different than animal species as well. We see them migrating north as well. I don't have enough knowledge about specificity of either of those two areas, but I just know in a broad sweep that that's happening.
Yeah, 100%. And yeah, the differentiation between peat plateaus and fens on the Hudson's Bay Railway is something that's very, very apparent. And there are a few papers floating around that discuss that more if you're interested in reading more about it. And even just seeing some of the images of the clear differentiation between um, the different areas. I mean, another thing that pops into my head is the fact that, especially if you're looking in like the Yukon, if you see certain types of trees, like typically like black spruce and that sort of thing, it's a good indication that there's permafrost in that region. And yeah, there's some excellent engineers that have great knowledge of picking up on those things that I am very envious of their ability to immediately
Yeah,
spot permafrost in certain regions.
yep,
Um,
definitely.
yeah, there's one more question here. What are the possible options to measure qualitative data? Um, I want to know about the gauge data or remote sensed data.
So in terms of qualitative data, and certainly I'm getting more and more experience with collaborating with people from geography. Um, we can certainly always look at change detection and look at optical data, whether that's from Landsat imagery. We can also look at it from radar imagery. And now more prevalent are drones or UAVs or UAS, depending on how we want to define them. Um, and certainly Frederick is doing a lot of work in that area in terms of collecting both optical and LiDAR data so that we can understand change detection, both in vegetation, but also in surface profiles. And then eventually we'll relate that to ground deformation. So we will conduct, in terms of that sense of other sensors, we will conduct a traditional engineering kinetic survey so that we can actually get profiles along the ground, along different transects, and get an idea of the elevation and ground truth it. We have the LiDAR data as well that will continue to fly. And all these techniques are also being used by different people along the Hudson Bay Railway. As you recall, there's many different universities involved, and they all have their expertise. And we're using both optical data and LiDAR data as well through airborne surveys. And also, Natalie has a large suite of different types of instrumentation at a bridge to trying to better understand both how the bridge piles are moving, how is the embankment moving relative to that, I believe also particle image velocimetry technique as well is being used. So basically taking images and just looking at those pixels change over time, and you can sort of detect motion. Gina and Adela have put in point source data loggers. They're very simple, cheap, but simple, but also time resourceful or time resource heavy. You actually have to physically go get them and then RFID the data from that. They're not automated downloadable data through the cloud, whether it's satellite or cell communication, but they're measuring temperatures, they're measuring pressure. So from pressure, we can also get an idea of the water levels, if we have the idea of the barometric pressures of the atmosphere, and also the profile of the cross section of the Engage River. So there's a number of also boreholes that are being instrumented that will have an idea. So we have an idea of the temperature profile with depth over time. And hopefully this year we will install our electrical resistant tomography. So we're going to get a better understanding of frozen versus unfrozen soils. And that would provide us with some understanding of where permafrost is or not existent. So talc, for example. And also I hopefully will be successful in getting a ground penetrating radar unit so that we can actually then correlate both the ERT data with our borehole data, so we know what kind of soil stratigraphy we have with the ground penetrating radar data, so we can relate that to sort of strength parameters like shear strength
Amazing. Thanks so much, Shawn.
and use
Just
that
to
in a
be
numerical model.
cognizant of the
Sorry.
time, I think we'll wrap it up there. Thank you so much to everyone who's still here for coming and listening to this amazing talk. Lots of super interesting information, lots of amazing pictures to see of different types of linear infrastructure. Um, Stay tuned. We're going to be having our next PYRN webinar towards the end of March. More information to come, but it will be with Brendan O'Neill from the Canadian Geological Survey, talking more about mapping and that sort of thing. But yes, thank you so, so much, Shawn, for agreeing to do this. And I hope that everyone got lots out of this.
No, thank you for